Hello everyone, I am Pawan Kumar R. Patil, working as Assistant Professor in Electrical Engineering Department, SITCOE. So today we are going to discuss about the solid state devices on this chapter, on this subject. We are going to have a discussion on power amplifiers. So let us take this one. Here, let us take an example of the public addressing system. In public addressing system, what happens? We do have multiple stages for amplifying the output. Let us see what is a public addressing system. It is nothing but the speaker system in which if you want to enhance the signal capacity, that is if a person is speaking, if you want to enhance that output, in that case we have to have multiple stages like this. This is stage 1, stage 2, stage 3, stage 4, like that. You can have multiple number of stages. Here stage 1, 2 and 3, here what is expected is the signal has to be amplified as much as possible. Fine. But in the last step, what is expected is the total amplified signal has to be given to the loudspeaker. For that, the basic requirement of the last stage is to deliver high power. For that, we are going to use a kind of amplifier called as the power amplifier, and that is what we are going to discuss here. Okay? So if this is a power amplifier, what about the other amplifiers? Here we will be using the normal amplifiers which are going to indicate, or you can say which are going to enhance the signal strength, and here we are going to enhance the output power capability so that more or you can say high power output will be delivered to the load. Okay? So in this case, that is power amplifier, we can classify that the power amplifier into 4 stages, that is class A, class B, class C and class AB. Okay? So what are these classes and all? Let us see. But before going for that, let us have a small revision on the basics which you have already learned in the class. That is, take for example the case of a common emitter configuration of the transistor. Common emitter means here the emitter circuit will be common for both input and the output. So this is the input side and this is the output side. For both of these things, the emitter is the common. Okay? Now here for the output circuit, this is our output circuit. Let us apply the KVL. According to that, the total VCC is divided into two voltages, that is ICRC and VCE. VC is nothing but the collector to emitter voltage. Fine. So according to this, we can write the equation, that is VCC is equal to ICRC plus VCE. This is our first equation, where RC is nothing but the load resistance. Now let us derive it for IC. So IC becomes, IC is equal to, if you take ICRC on the other side and VCC minus VC, like that, we'll get it as IC is equal to minus of 1 upon RC into VCE, minus of 1 upon RC into VCE plus VCC divided by RC. Okay? Here compare, let us call this equation as equation number 2. Now let us compare the equation number 2 with the equation of a straight line. So what is the equation of the straight line? The equation of the straight line is nothing but y is equal to mx plus c. That is written over here. Y is equal to mx plus c. So what is here? Y is a variable which is equal to mx, in that m is the slope of the waveform, or you can say slope of the line, and c is a constant. So when you compare equation number 2 with the equation of the straight line, we can find y is nothing but IC and m is nothing but minus of 1 upon RC, and x is equal to VCE and c is equal to VCC upon RC. Okay? So it means to say whatever equation which we have brought for the output is nothing but a equation of a straight line. So let us draw this straight line in the output curve. Okay? So using this, we can draw a straight line on the graph of IC versus VCE, that is output characteristics. So if you draw a straight line, that straight line is called as the output characteristics. For that straight line, minus of ICRC will be the slope, and its y-intercept will be VCC upon RC. Okay? And from equation number 2, when we can see that when VCC or VC is equal to VCC, in that case, that is nothing but the entire voltage is applied across the transistor. In that case, obviously IC is equal to 0. It means to say, when there is no current which is flowing, the entire voltage will be applied across collector to emitter. And in the second case, when VCE is equal to 0, that is, there is no voltage across this. In that case, there is no voltage across collector to emitter. In that case, IC is equal to VCC upon RC. Obviously, it means to say that whatever voltage which you are providing is being consumed by the load resistance. That's it. Okay? Let us go for drawing this straight line. Just now what I have told you, that the equation number 2 is nothing but the equation of a straight line. So that straight line we are going to draw. So where are you going to draw that? Let us see that here. Okay? So let us draw the straight line. Here the straight line will be this one. Whatever is drawn here, it is that straight line which you are talking about. Fine. So where are you drawing this total straight line? This one. Have you seen this one? We have discussed about this thing, this curve in the class. What is this? This is nothing but the output characteristics. And how are you drawing the output characteristics? Output characteristics nothing but it is the characteristics of IC versus VCE. Okay? How IC changes as VC changes. That's what we are going to see in the output characteristics. And it depends on which quantity? It depends on the various values of base current. If the base current is low, we may get one kind of waveform. If the base current increases, accordingly our total output is going to increase. Okay? Now let us draw the load line on this, or the straight line. The straight line is also called as the load line. So whenever, just now we have seen that when VCC is equal to 0 in equation number 2, when VCC equal to 0, in that case we can have the total maximum current is equal to VCC upon RC. Sorry, not VCC, that's the VCE is equal to 0. In that case, it is equal to VCC upon RC. Okay? And when IC is equal to 0, the total voltage will be VCC, or you can say the quantity which will be remaining over there will be VCC. So when we join both of them, we can have a straight line like this. Okay? And this straight line touches the total output characteristics at many points. It is going to touch over here, here it is touching, here it is touching, here and here. Whenever there is an output characteristics, in all the output characteristics, the load line is going to touch the characteristics, or you can say the output waveforms. Okay? Now, what do you mean by that? What is the significance of that? The significance of that is, wherever it is touching the particular output load, or you can say output characteristics, that indicates a point called as Q point. You can also call that as quiescent point, Quiescent, quiescent point. Okay? And particularly it will be expected at the middle of the line. Fine. So what is that Q point? Q point is the line or a point where the load line intersects the output characteristics. Okay? Now the collector current corresponding to Q point, let us call that as ICQ, and the collector to emitter voltage, let us call that voltage as VCEQ. Fine. So let us see what is the significance of that. Okay? Here IBQ. What is IBQ? IBQ is nothing but the base current corresponding to the point where we are indicating the Q point. Okay? And what do you mean by base current? Base current is nothing but that is what we are giving that as input to a transistor. Fine. So what is the importance of giving an input to the transistor? Obviously transistor is used for that purpose only. If you are providing any input, that has to be amplified. Whenever you are using a transistor as an amplifier, it has to amplify the signal. No? Which signal are you going to amplify? It is nothing but the signal which you are providing at the base, that has to be amplified. Okay? Now that signal may change like this. As that signal changes, the corresponding collector current changes and the collector to emitter voltage also changes. Actually what happens when that base current is going to change, first the collector to emitter voltage changes, correspondingly the collector to or collector current is going to change. So both things are indicated in the diagram. Okay? So what is again the significance of this? Let us put these things on the load line, or you can say output characteristics. Okay? So here we do have the load line. Let us take this diagram. In that we do have the load line. Here I have indicated the Q point. So first what happens? The base current is going to change for some values. For that we have these characteristics. So let us consider the base current is changing in this manner. So correspondingly what has to happen? As just now I have told you, correspondingly the voltage has to change, and you can see there is a phase shift of voltage and currents. What do you mean by phase shift? As the voltage changes, the current changes in the inverse manner. So it means to say that they are phase shifted by 180 degrees. You can say the same characteristic over here and here. So what is happening? The base current is changing. Accordingly, the total collector to emitter voltage is also changing in this manner. Okay? So correspondingly we can see the collector current also swings. So when the base current changes, the voltage changes and the current changes. Or which current? The collector current. Okay? So this is the normal characteristics, and the base current is corresponding that will be IBQ. So this is the normal operation of a transistor working as a power amplifier. Okay? Let us go for the next characteristics. As I told you, how many kinds of classification are there? There are total 4 classifications: class A, that is class A, class B, class C, and class AB. So let us go for discussing those things. So in this diagram we can have all those 4. So this is class A kind of power amplifier, this is class B, this is class C, and this is class AB. So let us discuss about the first one. Class A indicates what? Class A indicates, as you can see from the diagram, it can operate for 360 degree operation. 360 degrees means according to Q point. Q point will be at the middle of the load line. See, this is the load line. Q point will be exactly at the mid of the load line. Because of that, as the voltage changes from 0 to 360 degrees, the corresponding current also changes from 0 to 360 degrees. So complete 360 degree operation we are going to get for this one. Okay? So this is the first class, which is class A. And when you go for discussing class B, in class B, as you can see, the Q point is exactly on the VC, or you can say exactly on the x-axis. So if the Q point is on the x-axis, what kind of output we are going to get? We are going to get only half cycle of the output. Understood? What is happening in class A? In class A, we are going to have a total 360 degree operation, and in class B, we are going to get only 180 degree operation. That is, maybe it is only positive half cycle, depends, maybe it is negative half cycle. But the thing is, the voltage positive half cycles will be getting, and the collector current negative half cycle we will be getting. Okay? And coming back to the class C, in class C, what is the position of the Q point? The Q point is below the, or you can say beyond the VCC line, or you can say beyond the x-axis, or you can say below the x-axis. Because of that, what is happening here? We are not getting even complete half cycle also we are not getting. A part of that is going to be cut. So only few, or you can say very short duration of cycle we are going to get at the output. Okay? And when you go for class AB, it is nothing but it is transition from class B to class A. So here we are not going to get exactly half cycle, we are going to get little bit beyond that, and not going to get complete cycle. Here we are going to get, in class A we are going to get 360 degree operation, in class B we are going to get 180-degree operation, and in class AB we are going to get an operation which is between 180 degrees to 360 degrees. That is what we are going to get at the class B. Okay, so this is the basic classification of the power amplifier. So what is the significance of all these things? The significance of all these things is these all classes, class A, class B, class C, class D, or class AB, sorry, are going to be used for amplification purpose only. But the thing is, if you use class A, it is going to work for entire 360 degrees. It means whatever amount of input you are getting, the exact output you will be getting, maybe amplified thing. Okay, so the disturbance will be a little bit less in that. And when you go for, or you can say you are going to get a complete cycle of that. When you go for class B, only half of the output you are going to get. Class C, you are going to get even less than half of the cycle. And when you go for class AB, it is more than half cycle, but it will be less than the full cycle which you are going to get. Okay, so in summary, we can draw the summary like this. Comparison of power amplifier classes. Here we can have the classification for as A, class B, class C, and class AB. So for these classes, what is the operating cycle? As I told you, class A operates for 360 degrees, class B operates for 180 degrees, class C operates for less than 180 degrees, and class AB operates for 180 to 360 degrees. Okay? Next, position of Q point. As I told you, in class A, the position of Q point will be at the center of the load line, and position of B will be on the x-axis, and in class C, it is below x-axis, and in class AB, it is above x-axis but below center of the load line. Obviously, it should be between A and B only. Okay? And when you go for the efficiency, it is most important part. The efficiency of class A amplifier is very less, that is up to 25 to 50%, and that is of class B will be 78.5%, and class C will be high, it is almost around 90%. Okay, it is not written there, but it is around 90%. And when you go for class AB, the efficiency varies from 50% to 78.5%. that is nothing but class A to class B efficiency you are going to get. So we may get a question that in class A we are going to get a complete 360-degree operation, but the efficiency is less, and in class C we are not going to get any even half of the cycle, but still we are going to have a 90% of efficiency. How is this possible? See, efficiency is different, the total waveform which you are going to get at the output is different. Efficiency means what? In the input, whatever part you are considering for the output, exact output you will be getting. It is nothing but you are amplifying that. In C, what is happening? Only a small part of output you are getting, but whatever the corresponding input is there, that exact output you are going to get, that exact will be converted to around 90% of that waveform you will be getting at the output. But when you go for class A, in that case, maybe whatever is the input, due to distortions, you are going to get the poor output you are going to get. Because of that, we can say that the efficiency of class A is very less. Okay, so this is the discussion on the power amplifiers. Okay, thank you.